In this video, we will solve principal stress problems. First problem, well, in point A, find the principal stresses. You see, we have here a bent profile, and this section is also given, and the dimensions can be seen over here. The first thing we have to do is we have not a very simple section. We draw this section, and for this section we have to determine first of all the area, the position of the centroid, and the moment of inertia around this centroid, and we have also determined the Q values. For example, for point A, we will come to that point later, but since it is on the surface, the area when you draw a line through A is only 0 and your Q is 0 on the surface. Well, these properties of this section we need for stress calculations. Now, to determine the internal loadings, we have to cut, and when we cut over here, possible internal loading are a normal force, a bending moment, and a shear force. So we do not know these values. We have to determine these values with the help of equilibrium equations. So the external load is 6 Newton and the horizontal is 3 to 5, 6, and this one is 4 to 5 times 6. That's 4.8, and this is 3.6. Now the equilibriums. Well, if you take sigma x and y axis like this, sigma fx equals to 0, that gives you n minus 3.6 equals to 0, n is equal to 3.6. That's what we have determined. And what about sigma fy equals to 0? In this case, we have 4.8 minus 4.8 minus v equals to 0, v equals to 4.8. Well, these are not complicated calculations. We have found this. So now we come to the bending moment. Well, in this case, sigma m, let's call the centroid C, sigma mc equals to 0. Here you have first your m value, this value, and then the bending effect of the external loads. Like, well, this force is trying to rotate in the negative direction minus, that will give you 4.8 times 0.8. And what about the other component? The other component is this one. It tries also to rotate in the same direction minus 3.6 times 0.3991. So here you can calculate the m value, and you will find that m is equal to 5.37. You have your normal stress, you have your shear stress, you have your bending moment. So the normal stress is created by normal forces and bending forces. So in point A. Let's calculate the normal stress. We have a compression over here. That's minus 3.6. That is in kilonewtons. And this is the area of the sections which we have calculated beforehand. And what about the bending? M, the bending moment is, let's say, acting like this. So in point A, which is over here, in point A, well, the effect of such a bending is negative in the lower fibers and positive in the upper fibers. Then you will have negative bending moment, the distance to the neutral axis, and that is the moment of inertia. And the sigma is calculated as the sum of these two effects. The first one is the effect of the normal force, and this is the effect of the bending. The result will give you minus 70.8. So what about the effect of the shear force? You have a section like this, and your shear force is acting in this direction, and its value is 4.8 kilonewtons. So when you have a shear force, we know that on the upper and lower surfaces, value of the shear stress is 0. It's maximum on the neutral axis. My point A lies over here, so I have to write down directly that the tau in point A is 0. So calculate the principal stresses. You see, well, you can easily write that the stress state in point A is minus 70 and 0 tau. So this is this surface, and it has a very simple stress state. Well, this 70 is also principal stress. Why? Because on this surface there is no shear stress, and principal stresses are acting on surfaces where the shear stress is 0. So my minus 70 is the principal stress. The other one in this direction is 0. And there is a third principal stress, which is perpendicular to the plane of the screen, which is also 0. Minus 70 is the smallest one, and the others are 1, 2, and 3. Another problem. Well, determine the principal stress at point A in section AA. Okay, another section. This time we are interested in point A. Well, this may be more complicated to determine the shear stress and bending. Let's see. Okay, this is the critical section. We have to determine the stresses or the internal loadings in the sections. First, in this case, we have some supports, and we have to calculate the support forces. When you do this calculation, support reactions, so I will not go into detail, you write sigma MB and you find this value, FCD, and writing sigma Fx and sigma Fy equal to 0, you determine the two support forces, Bx and By. So we have determined the three unknowns. Now we go to my section AA, where we cut through this section and take this left side, and this is my left side. And we know in point B, I have determined the support forces. I can draw them and write down my X and Y axis, and in this case, sigma fx. Well, we have what? We have this force and this force. 1876 minus n equal to 0, n can be determined. Next, in the y direction, we have this force and we have this force. Here we have v minus 500 some, v equals 583, and the bending moment in this section can also be written by taking sigma m is 0, and here you have that m is 87.5 Newton meters. So these are my internal loadings in section AA. Next, well, here is the summary of what we have calculated up to now. We can calculate this section properties. The area, the moment of inertia around the centroid. Here we have a symmetrical section. Centroid is in the middle. So around this neutral axis, the moment of inertia can be calculated. We will not go into detail. And the Q value for the shear stress calculation. So when we have a shear force V, the shear stress in any point of such a section, well, in this case, we have point A. So for this, I have to know the shear force. I know it. I value, I know it. The thickness in this point, this is this thickness, and I have to determine the Q. How determine the Q? I have to draw a line through point A and calculate this area and determine the centroid of this area. I also have the centroid of the whole section. This distance is y bar prime. And so if you do this calculation, you find for point A that Q is 31875. So before stress calculation, the first I do calculate this section properties. They're ready. The stresses, well, the normal stresses are due to normal force and the bending moment. And in my case, I have a compression. So this is this value. And I have a bending, which creates a positive normal stress. And this value can be calculated with this formula. As a result, the normal stress in point A is 602, and the shear stress, we have no torque, so shear stress is only due to shear forces. So we know the shear force. We have calculated the Q value. I is known, T is known, and so we have the shear stress. So as you see, we have a stress state like this, and the normal stresses due to normal force and bending gives you a positive 6, and the shear stress is 1.55 megapascals. Now we know the stress state sigma x, sigma y, and tau xy in the plane. Now determine the principal stresses in the plane. Here we can use this formula, put the numerical values, and the principal stresses in the plane are 638 and minus 0.36. Well, we do not know whether these are 1 or 2 or 3, but we know there is another principal stress perpendicular to this plane, which is 0, so you can name this as 1, and this one as 2, and the last one as 3. These are the principal stresses in three-dimensional case. Next, what about the orientation of these principal planes? We again have a formula and we can calculate tangent to theta, and theta is found as 13.36. Well, you may not know whether this 1336 belongs to this one or this one. Case, you take this value, put into the stress transformation formula, and as you see, if you put your theta and sigma x values, well, the result gives you that this is 638. So the orientation of the principal plane is 13.4. It belongs to this plane, to this stress, and you can call it principal 1. Next, well, we can draw the principal planes and stresses. So at the beginning, we had a stress state like this. That was sigma x equal to 0. That is 6.02, and sigma y equal to 0. We had a tau value like 1.515. That was tau xy, and this stress state creates a principal stress of 638 and -36, and their orientation is, when this is your x, their orientation is anti-clockwise 13.4 degrees rotated. This is your principal 1, and that one is your principal 2. In this video, we have solved principal stress problem. You know that such problems can be also solved with the help of the Mohr circle. Well, about Mohr circle problems, we have a special video. Thank you for listening.